Hello, Math 1 students. We're on section 11.2, reflections. This is part 2. We did part 1 prior to spring break. So today we're going to look at glide reflections, and then we're going to identify lines of symmetry. So a reflection postulate says that a reflection is a rigid motion. Now, rigid motion means that length and angle measures are the same from the pre-image to the image. So even if you reflect it, that means the lengths of, say, a triangle don't change. The angles of a triangle don't change. You have a line segment, the length of the segment doesn't change. If you have an angle, the measure of the angle doesn't change. It's a rigid motion. The shape itself doesn't change. It just moves in the sense that it reflects. The composition theorem also applies and guarantees that any composition of reflections and translations is a rigid motion. So from section 11.1, the composition theorem says that if rigid motions are combined, then the final image is still a rigid motion. In other words, the shape doesn't change in length or in terms of angle measures. So let's look at what a glide reflection is. A glide reflection is a transformation involving a translation followed by a reflection in which every point P is mapped to a point P double prime by the following steps. So it's 2 steps. Step 1, a translation maps P to P prime. So you're starting here basically at this segment PQ, and the first step is that it moves up. So P goes to P prime, Q goes to Q prime. So you can see it moves a little bit to the right and then up. So the first step is the translation. Step 2, a reflection in line K parallel to the direction of the translation maps P prime to double prime. So you notice that line K is parallel to the direction that P and Q map to P prime and Q prime. So you can see those 3 segments are all parallel. So then you have a reflection across that line. So Q prime becomes Q double prime, P prime becomes P double prime. Example 4a, graph triangle ABC with vertices A3, 2, B6, 3, and C7, 1 and its image after the glide reflection. So the first step is a translation where x, y becomes x minus 12, y, and then the reflection is in the x-axis. So here's our triangle, A, B, and C. A is at 3, 2, B is at 6, 3, C is at 7, 1. The first step is a translation 12 units to the left. So A from 3, 2 goes to A prime, negative 9, 2. So A moves 12 units to the left. So the translation is directly to the left. B goes from 6, 3 to B prime, which is at negative 6, 3. And C goes from 7, 1, 12 units to the left, to negative 5, 1. So the first step in a glide reflection is a translation. So this is the first transformation. The translation goes directly to the left. Step 2 is a reflection in the x-axis. So I highlighted the x-axis in pink. Notice that the direction that A, B, and C translated directly to the left is parallel to the x-axis. So the rule for the x-axis is x, y becomes x, negative y. In other words, the x-coordinate stays the same, but the y-coordinate gets flipped. So A goes from negative 9, 2 to negative 9, negative 2. So the x-axis is a line of symmetry. A prime is 2 units from the x-axis, so A double prime has to be 2 units below. B prime goes from negative 6, 3 to B double prime, which is negative 6, negative 3. So B prime is 3 units away from the x-axis, so B double prime has to be 3 units below the x-axis. Same distance in the opposite direction. C prime is at negative 5, 1, so C double prime has got to be 1 unit below the x-axis at negative 5, negative 1. Connect those dots and you have the triangle indicating the glide reflection. Now notice this was a glide reflection because the translation was horizontal, directly to the left, and the subsequent reflection was across a horizontal line. So just because you have a translation followed by a reflection doesn't make it a glide reflection. A glide reflection requires a translation and a subsequent reflection across a line parallel to the direction of the translation. All right, here's 4b. We're going to start out with the same triangle, and now you guys are going to try this. We're first going to do a translation where xy becomes x comma y minus 4, and then the reflection in the y-axis. So take a moment to give this a shot. So A, B, and C is the same triangle we started with, and now we're first going to translate 4 units down. So A goes from 3, 2 to A prime 3, negative 2, so 4 units down. B goes from 6, 3 to 6, negative 1, 4 units down. C goes from 7, 1 to 7, negative 3, 4 units down. So the first transformation is a translation vertically downwards. Step 2 is a reflection in the y-axis. Notice the y-axis, which is highlighted in pink, is parallel to the direction of the translation, in which case it was straight down, so the y-axis goes up and down, it's parallel. So the rule for a reflection in the y-axis is that x comma y becomes negative x comma y. In other words, the y-coordinate stays the same, but the x-coordinate becomes flipped. So A prime, which is at 3, negative 2, goes to negative 3, negative 2. Notice A prime is 3 units to the right of the y-axis, so the reflection means A double prime is 3 units away, but to the left of the y-axis. B prime is at 6, negative 1, which means B double prime is at negative 6, negative 1. B prime is 6 units from the x-axis. B double prime is 6 units away the other direction. C prime goes from 7, negative 3 to C double prime, which is negative 7, negative 3, 7 units away from the y-axis in the same direction. There is your reflected triangle completing the glide reflection. So glide reflection, again, is a translation followed by reflection in the same direction as the translation. Our last topic is the line of symmetry. A figure in the plane has line symmetry when the figure can be mapped onto itself by reflection in a line. This line of reflection is a line of symmetry, such as line M. A figure can have more than one line of symmetry. So line M is the line whereby if you folded that butterfly across line M, it would overlap itself. In other words, if you can fold the figure in such a way such that it perfectly overlaps over itself, that fold represents a line of symmetry. Now keep in mind, depending on the shape, depending on the figure, you can actually have many more than one line of symmetry. For example, if you have a circle, there are infinite numbers of line of symmetry because no matter where you draw a diameter, you can fold a circle onto itself. So let's take a look at these last 6 examples, and we're going to count and draw the lines of symmetry. 5a, how many lines of symmetry does this shape have? So this is a hexagon. So notice there are 2 lines of symmetry. You can draw one across, cut it in half across, and the hexagon would fold over itself. You can also have one going straight up and down, where if you folded the hexagon over that vertical line, you again have overlapping halves. 5b, how many lines does this shape have? So this is a regular hexagon. So this has 6 lines. So notice you can fold it in 6 different places, and the hexagon would overlap itself perfectly. So you can fold it over, say, a vertex. So you can do this, and you have 2 halves of a hexagon. You could also fold it in between vertices. Whoops, that's a little messy. Let me make it a little clearer. And then you can fold it over itself perfectly, and those happen 6 different places. How many lines of symmetry does this figure have? Take a guess. Well, there's only one. It's the one that cuts through the middle horizontally. So if you fold that shape horizontally across that line, it overlaps. There's no other line where you can draw where if you fold it over that line, the shape will overlap itself perfectly. You have a rectangle. How many lines does this have? Again, it's only 2. There's the one cutting across in the middle horizontally, and there's one cutting across up and down. How many lines of symmetry does this pentagon have? Turns out there are 5. So here they are. You can go up and down. You can go across through one vertex and through the midpoint of the opposite side. You can draw 5 different lines of symmetry through this pentagon. So it'd be 1, 2, 3, 4, 5. Finally, how many lines of symmetry does this triangle have? In this case, there's only one. It's the one cutting through the middle vertically. Notice if you try to draw it like that, it won't work. So there's only one line of symmetry for this triangle. Now keep in mind, not every shape has a line of symmetry. So that's it for section 11.2 part 2. If you have any questions, feel free to email me or ask me questions during office hours.